The Gram-Schmidt orthogonalization process is an approach to find an orthonormal basis to a given basis of an Euclidean vector space. Before I explain the orthogonalization process, I want to define what an Euclidean vector space is and what it means for a basis to be orthogonal. First of all, I will tell you what an Euclidean vector space is. An Euclidean vector space is a vector space V over the field of the real numbers together with a so-called scalar product. A scalar product is a function from V cross V to the real numbers, which is denoted like that here, that satisfies that it is bilinear, that it is symmetric, which means that the scalar product of x and y is the scalar product of y and x for every xy in the space V, and that it is positive definite, which means that the scalar product of x with itself is larger or equal to 0, and it is 0 if and only if x is equal to 0. By using that scalar product, you can define a norm on the vector space V. That particular norm is called the Euclidean norm. It's given by the square root of the scalar product of a vector x with itself and denoted like that. So the Euclidean norm of a vector x in the space V is equal to the square root of the scalar product of x with x. Now I want to tell you what an orthogonal basis is. Let V be an Euclidean vector space. And that here is the scalar product on that vector space V. And let B is equal to B1 to Bn be a basis of that vector space V. The basis B is called orthogonal basis of the space V if the scalar product of Bi with Bj is equal to 0 for I is not equal to j. The basis B is called orthonormal basis of the space V if the scalar product of Bi with Bj is equal to 0, for I is not equal to j, and the scalar product of each vector Bi in the basis B with itself is equal to 1. That here means that the Euclidean norm of each vector Bi in the basis B is equal to 1. Now we will take a look at the Gram-Schmidt orthogonalization process that tells us how to orthogonalize a given basis C. Let V be an Euclidean vector space of dimension n with a basis C is equal to V1 to Vn. Then there exists a basis B is equal to B1 to Bn with the scalar product of Bi with Bj is equal to 0, for I is not equal to j, which means the basis B is orthogonal. You can use a formula to find the vectors Bi in the orthogonal basis B. So we set B1 as V1, which is the first vector in the basis C. Then that here is the calculation formula for Bi. Bi is equal to vi minus the sum from j is equal to 1 to I minus 1 of the scalar product of vi with bj divided by the scalar product of bj with bj times bj for I is equal to 2 to n. You also have that the space of all linear combinations of v1 to vj is equal to the space of all linear combinations of b1 to bj, for j is equal to 1 to n, which can be written down like that here. If you have found the orthogonal basis b by using that calculation formula here, it is easy to write down an orthonormal basis b bar. You just have to normalize the vectors in the basis b. So the orthonormal basis b bar is equal to b1 divided by the Euclidean norm of b1 to bn divided by the Euclidean norm of bn. So that here is an orthonormal basis of the space capital V. Let's take a little closer look at that formula here, which calculates the vectors in the orthogonal basis B. So the first vector b1 in the basis is just v1. The second vector b2 is equal to v2 minus the scalar product of v2 with b1 divided by the scalar product of b1 with b1 times b1. We have used that general formula here for I is equal to 2 to find that here. The third vector b3 is equal to v3 minus the scalar product of v3 with b1 divided by the scalar product of b1 with b1 times b1 minus the scalar product of v3 with b2 divided by the scalar product of b2 with b2 times b2. Here we have used the general formula for I is equal to 3. And so on. So this is how the general formula is used to calculate the vectors in the orthogonal basis B. Let's take a look at an example now. Let V be R2 with the standard scalar product. That means the scalar product of x and y is equal to the first entry x1 times the first entry y1 plus the second entry x2 times the second entry y2. This scalar product here is called the standard scalar product in R2. We have given the following basis C of R2. So C contains the vector 1, 1, which is v1, and the vector 2, 1, which is v2. We want to find an orthogonal basis B with respect to this basis C here. So we use the Gram-Schmidt Orthogonalization process on C. So our formula tells us B1 is just equal to V1, which is the vector 1, 1. The vector B2 is equal to V2 minus the scalar product of v2 with b1 divided by the scalar product of b1 with b1 times b1. So we have to calculate two scalar products, this here and that here. So we have to calculate the scalar product of v2 with b1, which is equal to that here. So this here is v2 and that here is b1. And by using this here, we get that this scalar product here is equal to 2 plus 1, which is equal to 3. Now we have to calculate the scalar product of b1 with b1. So this is equal to that here. And by using this here again, this calculation rule here, we get that this here is equal to 1 plus 1, which is equal to 2. Now we can plug everything in the formula here. So in the end we get that b2 is equal to 2, 1, which is v2, minus 3 divided by 2, so 3 is that here, and 2 is that here, times b1, which is 1, 1, 1, 1. And when we solve this here, we get in the end that this here is equal to 1 divided by 2 times the vector 1 and minus 1. So this here is our vector b2. So our orthogonal basis b is equal to b1 and b2, and this is equal to that here. So b is our orthogonal basis we were looking for. If you're looking for an orthonormal basis, you have to normalize b1 and b2. So you need to calculate the Euclidean norm of b1 and b2. So the Euclidean norm of b1 is that here, and this is equal to the square root of 2. The Euclidean norm of b2 is equal to that here, which is equal to 1 divided by 2 times the square root of 2. Now that here is your orthonormal basis. So b bar is equal to b1 divided by the Euclidean norm of b1, which is that here, and b2 divided by the Euclidean norm of b2, which is that here. In the end, you get this here. So that here, b bar, is an orthonormal basis for R2. Let's take a look at something more difficult. Let V be R3 with the following scalar product. So the scalar product of x and y is equal to x transposed times A times y, where A is the following matrix. You have to find an orthogonal basis B of R3 with respect to that particular scalar product here. So normally you would now have to check if that here is really a scalar product. So if that bilinear form here is symmetric and positive definite. But in our case, the example already tells us that it is a scalar product. So we just trust that this here is a scalar product and move on to the orthogonalization process. For the orthogonalization, we need a given basis C of R3. In this case, we can choose our basis C ourselves. We will choose the standard basis of R3. So C is equal to the standard basis of R3, which looks like that here. So this here is V1, that here is V2, and this here is V3. Now we start our orthogonalization. So we set B1 as V1, which is equal to this vector here. Then B2 is equal to V2 minus the scalar product of V2 with B1 divided by the scalar product of B1 with B1 times B1. So we have to calculate this scalar product here and that scalar product here. So we have to calculate the scalar product of V2 with B1, which is equal to V2 transposed times A times B1. And this is equal to 1, because B1 and V2 are both unit vectors. So B1 is this unit vector and V2 is that unit vector. This here is just that entry of the matrix here, because V2 and B1 are unit vectors. We also have to calculate the scalar product of B1 with B1. So this here is equal to that here, B1 transposed times A times B1. And this is equal to 2, because B1 is a unit vector. This here is that entry of the matrix here, which is 2. Now we plug everything in the formula here and get that this here is equal to that here. So that vector here is V2. This here is 1. That here is 2. And that here is the vector B1. So in the end, we get that this here is equal to 1 divided by 2 times the vector -1, 2, and 0. So this here is our vector B2. Now we will calculate B3. So that here is the formula for B3. And we have to find these scalar products here. This here, that here, this here, and that here. So we start to calculate this scalar product here. So we have to calculate the scalar product of V3 with B1, which is equal to that here, V3 transposed times A times B1. And this is equal to 1, because B1 and V3 are unit vectors. This here is just that entry of the matrix A here. So this here is equal to 1. Because we have already calculated the scalar product of B1 with B1, we will now calculate the scalar product of V3 with B2. So the scalar product of V3 with B2 is equal to V3 transposed times A times B2. Because V3 is the third unit vector, we just have to insert B2 in the last row of A. So we get 1/2 times -1 times 1 plus 2 times 1 plus 0 times 3. So we just have to insert B2 in the last row of A, because V3 is the third unit vector. So in the end we get that this here is equal to 1/2. Now we need to calculate the scalar product of B2 with itself. So the scalar product of B2 with B2 is equal to B2 transposed times A times B2. And B2 is that vector here. So the first thing we do is to plug in B2 in the matrix A. So we get this here. By solving this, we get 1/2. So the scalar product of B2 with itself is 1/2. The last thing we have to do is to plug all these values in the formula for B3. So we get that B3 is equal to that here. So this vector here is B3, this here is 1, that here is 2, B1 is equal to that vector here, and this here is 1/2 divided by 1/2. So this here becomes 1. So in the end we get minus B2, which is that here. By solving this, we get the vector 0, -1, and 1. So the vector B3 is equal to that vector here. Now these three vectors, B1, B2, and B3, form an orthogonal basis of R3 with respect to that particular scalar product. If you want, you can now normalize these vectors B1, B2, and B3 by dividing them by their Euclidean norm. You can try this out yourself as an exercise. Okay, I hope you now understand how to use the Gram-Schmidt orthogonalization process on a given basis C to find an orthogonal or orthonormal basis of an Euclidean vector space V. If you liked this video, please consider subscribing to my channel. It would help and motivate me to keep creating videos.